Great. Thank you everyone for coming to our weekly seminar. So today it's our great honor to host the talk by Larry Carin and from the Chaos University. He's the provost there. So I know Larry was the first time, I forgot which year was that, but I've been with, I was a Young Investigator Award winner, and now I'm no longer young, but I was, and from Office of Naval Research, ONRYP. So then I got continuous grants after the war. So Larry, I believe, their team has a strong connection to Navy as well. So we had the annual meetings at least a few times at Duke. So I get a chance to meet with Larry and his students and colleagues and enjoying the campus and the nice food at Duke every year. So it was a very good experience. And so a bit of introduction about Larry. So Larry graduated his PhD from University of Maryland in 1989. And so since 1995, Larry has joined Duke and been there since until last year when he started his job as a provost at the Chaos. So at Duke, he left the position at Duke as a VP of research and vice provost, I believe. Yeah. So Larry is a very well-known researcher in machine learning and AI in general, and he published very extensively in major machine learning conferences. And in fact, if I remember correctly, Larry is probably the world most productive, or one of the world's most productive researchers in machine learning in terms of publications, SML and neurals. And so today, Larry is going to give a talk on GAN memory for lifelong learning. This is a very nice topic because quite a few people from my team actually working on that topic. So we're very excited. And welcome to Baidu, Larry, and please start your presentation. Thank you.
Okay, so Ping, thank you so much, and thanks for having me. And good morning, good afternoon, good evening to everybody, depending on where you are. So I want to just briefly note that this is joint work with Yulei Kong and Miaoyun Zhao, who were both postdocs with me at Duke. They're currently in China. I think they're on the call. I know Yulei is on the call. So if I get stuck, I'm going to call on Yulei. But in any case, so the focus of this talk is lifelong learning and using GAN as a tool to constitute memory in the context of lifelong learning. So we'll go through this. So so this is what we're going to cover. So we'll give a quick background on what lifelong learning is, and then explain some of the challenges, which are relatively well known. And then we will talk about how GANs can be used to constitute memory that is very effective and very efficient for lifelong learning. We're going to focus on image analysis in this talk, but the framework should be applicable to other settings. And so then we'll go through the GAN memory and then some final remarks. So so deep neural networks are of course widely used today and have been successful, but they require a large quantity of data, and it's essential that data is appropriate for the task at hand. What happens is that when systems are deployed in the real world, and they undertake different tasks, the data statistics can change, and consequently, the data that you trained on previously may not be appropriate for the new task. And so this is something we always have to be careful of. So, one solution of that is just always train on new data, always train on data for the new task. But the problem with this is that, first of all, the amount of data you have for a new task may be limited. And it's also wasteful of the data that you had previously and the experience that you had previously. People, or most biological systems, they continually learn over a lifetime, and information that they acquired or knowledge that they acquired in the past is transferred to the future, even if it's not exactly, if the future is not exactly the same as the past. So consequently, it's appropriate, it's desirable in the context of machine learning and deep learning to appropriately leverage what we've learned from the past and push it forward to new tasks over time, such that we share what we sometimes call statistical strength. So, so lifelong learning is, as you know, a widely studied area of machine learning, and it seeks to address this challenge. So, of course, this is just cartoon, so just for fun, but you know, you have an agent that is encountering multiple tasks over time, task 1 through task 3 here. There's associated data that you might train with, you know, data 1, data 2, data 3. And what you would like is, you would like an agent that would continually learn over time, so that as it sees new tasks, it's able to learn to do those new tasks, but also to retain the capacity to do the prior tasks, and also the capacity to transfer information from the past to the future to improve learning, and such that ideally the amount of data that you would need in the future would be less than what you would need in the past, because you have the capacity to appropriately transfer. So this is the goal. Now, this is a widely, you know, studied problem, and there's some fundamental challenges that motivate that study. And the most widely known of those is catastrophic forgetting. And so, so here, you know, we have 3 tasks, task A, B, C, and we first do task A, then we're given data for task B, and then we refine the model on data for task B, and then we go to task C, and then we refine the model for task C. And what happens is, over time, and this is what happens with deep neural networks, what happens is, by the time you get to training on task C, you have significantly undermined your capacity to do task A. And so this is called catastrophic forgetting. It's widely known in deep learning, but it's actually not surprising at all. When we do stochastic gradient descent to do learning, if we're only learning a given task on the data for that task, and we're not doing gradient descent on prior data, which is actually what you would want, right? Because you don't want to have to carry around with you all of the prior data. As the number of tasks increases, it becomes too expensive to have to retain all of the data. And so what happens is, when you do stochastic gradient descent, you're not using all of the data, and consequently, the model loses the capacity to perform prior skills or tasks. So this is a well-known problem, and there have been many attempts at trying to address this. We're going to address it using GANs, but GANs have their own challenges. So what we're going to do is try to modify GANs such that it's particularly well suited for lifelong learning in a way that we'll talk about in a second. So, so the idea is that GANs, generative adversarial networks, have the capacity to learn generative models that are capable of producing highly realistic data. And again, the focus here is on images, but this could be applied as well to text, or to natural language processing. So the idea is that if GANs are very good at learning the capacity to synthesize highly realistic images, maybe we can use these GANs as a tool for memory without having to retain all of the prior data. Now, what this implies is that we're going to have to continually learn GANs over time, over our multiple tasks, to achieve the goal that we want. That has its own problems, because if you think about what we've done is we've basically transferred the problem to now we need to do lifelong learning of GANs, right? If we could do lifelong learning of GANs, then we could use those GANs to do things like classification or other types of subsequent tasks. So that problem, doing lifelong learning for GANs, is relatively understudied. And that is the focus of this talk. So what we would like to do is to use generative adversarial networks to sequentially memorize the generative process of diverse data sets and grow the capacity of the GAN such that we can address increasingly complex data and different types of data. But we want to do this in a way where we have absolutely no forgetting of prior tasks or prior generative processes. And we also want to be able to do this for very diverse types of data, so perceptually distant target data sets. And we like to do this in a very efficient way, such that we can get compression. And so this is the idea of our work. So this is an example. So if we have tasks, different tasks, where, for example, we might be interested in faces, another task might be interested in flowers, castles, cats, CT images, etc. We would like to be able to learn a generative adversarial network over time, over these diverse data sets, in a way that is computationally efficient and for which we have absolutely no forgetting of the capacity to learn prior generative data or to constitute prior generative data. And this is what we're going to do. This is kind of a summary. So if we have here just 3 tasks, task 0 to 1, 2, and we're gonna acquire or see these sequentially. What we would like to do is to build a generative adversarial network, or GAN, that is capable of synthesizing all of these through this basically the same GAN model, or something very close to this GAN model. And as you know, so just for those, I think most of you know, so in the GAN model, what we do is we draw a random variable Z from a isotropic Gaussian distribution. We send that through a deep neural network, and then at the output of that neural network comes the data here, images. So this is our generator. In GANs, as I'm sure most of you know, we have a generator and we have a discriminator. I'm going to be focusing on the generator here, just in the presentation. But of course, we have to do lifelong learning of the generator and the discriminator. We have to do that over time. So I'm going to focus on the generator because the generator is the final product that we care about. It's the memory. It's our memory unit. But in the context of learning, we have to do this both on the discriminator and on the generator of the GAN. So again, I'm assuming that you know what GAN is. So this is our goal. All right. So let's now dive in. So now I need to just tell you a few details of the deep neural network that we're going to use, just so that you can understand the context, and also so that you can understand the notation that I'm going to use below. So again, we have a discriminator and we have a generator in the GAN model. I'm only going to focus here on the generator, but the discriminator is very similar. So we draw a random variable Z from an isotropic normal distribution. This goes through a fully connected layer at the top, and then a sequence of residual blocks, which each of these residual blocks, so this is block 0, block 1, block 6, each residual block is composed of leaky, ReLU, and convolution step. Okay, so these exist in each residual block. We call this layer 0 and layer 1 of the residual block. You'll see later where this comes up. Okay, so I'll come back to this a couple of times, but this is going to be the model that we're going to use. The discriminator takes the data as input and goes essentially in the opposite direction. And the discriminator has a similar structure. So the challenge that we would like to, what we would like to do is, can we, for example, build a GAN model for faces? So I think these might be celeb A faces. I'm not exactly sure, but in any case, a data set of faces. And so assume that we have a large data set of faces and that we can learn a GAN model for those faces. And so remember the model here. Okay, so just this is summarizing that. We have a fully connected layer, and then we have a whole series of convolutional layers. The fully connected and convolutional layers have, of course, weights. We're using different fonts for the weights of the fully connected layer and the weights of the convolutional layer. The question is, if we can learn a GAN model using a large amount of data for faces, can we modulate in an efficient way the parameters of the fully connected and convolutional layers so that we retain much of our original model? We do some sort of efficient modulation of the parameters. And then with minor change to the model, we can produce images of very realistic flowers, cats, CT images, X-rays, castles, cartoons. These images that you see here, this is not, these are not cartoons, although maybe it is. These are real synthetic images. This was produced by GAN. And so what we did here, and I'm going to show you how we do this, we took a large database of faces. We learned a GAN model, and then we came up with a framework whereby we can modulate the parameters of the model, of the generator. And then after that modulation, we can produce images that look quite different than the original image. And so what this implicitly tells us is that although the images look very different, the face images are very different, for example, than the CT images or these cartoons, there's fundamental structure in images, which is shareable and transferable between different data sets. And that's implicitly what we're exploiting here. Okay, so the question is, how do we do this? Let's focus on the convolutional layer. And by the way, at the end of the talk, I'm going to give you all the references. So if you can't follow all the details, that we've published this, and we'll give you the references at the end.
So may I ask a question here?
Of course. Go ahead.
Okay. My question is that you named the module as semantic modulation, right? So, yes. But it's well known to us that for any deep learning network, some layers represent the low-level features, yes, some other levels represent the high-level or semantic features. So my question is, why do you apply the modulation to each layer of your generator module here?
Yeah, so it's an outstanding question. Thank you for that.
Thank you.
So in fact, I was purposely kind of avoiding that because it was, I'm going to get to that later. I'm actually going to talk about that later, but let me talk about it now.
Sure, no problem. Thank you.
No. Let me, it's a real good question. And so let me talk about it, but I'm going to talk about it more later. So the point of that question, which was a very perceptive question and very good question, is that all layers in this network are not the same. And there may be some layers in this network that are very general and very transferable and may be transferred with very little modulation. And then there'll be other layers which will be very semantically dependent on the particular data being studied. And for those, we would expect significant modulation in the model parameters. Now, there's two things here, and I'm going to talk about, I'll just say a couple more about this. I don't want to have to a person, decide which layers are need to be changed semantically and which layers are transferable across all images. I don't want to do that because while the intuition is right, I don't know exactly which layers are which. And so therefore I want a model that can figure that out by itself. And you'll see at the end, it will figure that out by itself. But to answer your question a little bit, or not to answer, just to talk a little bit more, which layers of the generative model would we expect to be transferred with minimal variation? And which layers would we expect significant variation? So and it's a very important question, and we're going to see this empirically at the end. But let me just give you a hint. The layers of the network, which are very close to the data itself, to the output image, these correspond to very fundamental, the filters correspond to very transferable and general filter elements. And so therefore, what we will see, and if you think about this deeply, you can kind of anticipate that the layers near the output data are going to be very transferable, very generalizable. Whereas up near the top, these are maybe semantic types of constructs, which are very dependent on the particular data we're going to consider. So what we will see when we look at the empirical results is that the semantic modulation will be very significant at the top layers and will be very minor near the output. But the thing is, I don't want to have to choose which is which. I want the model to figure this out for itself, and it does. Okay, so I hope that answered the question. It's a very good question. We'll come back to it, okay, when we look at the empirical.
Thank you.
But I hope I answered your question fairly well. Okay, but at this point, I'm going to assume every layer can be modulated because I don't know which ones can and which ones can't. And I'm just going to let the model figure it out. If modulation is not needed, then there will be no modulation or very little modulation. If modulation is important, it will modulate it. All right, so let's look at the convolutional layer. We're going to do the same thing for the fully connected layer, but let's just talk about the convolutional layer. And W are the weights. The dimensionality of the weights are C out times Cn times K1 times K2. K1 and K2 are the number of pixels in each of the two dimensions of the filter. So there's two-dimensional planar space of the feature map. So K1, K2 is the geometrical size. Cin is the number of feature maps from the prior layer of the deep neural network. So whenever in the deep neural network, you go layer to layer, and that there are a certain number of feature maps or filters from the previous layer, that's Cin. And then C out is the number of filters going to the next layer. So C out is the number of filters going to the next layer. C in is the number of filters from the prior layer. K1, K2 is the physical size of our filter. Okay, hopefully that's clear. That's the weights. What we're going to do, we're going to calculate the mean and standard deviation, M and S, where we average over the support, the spatial support of the filter. So M is basically the average strength of the filter over its support, K1, K2, and S is its standard deviation. What we're going to do is this thing over here, we're going to do weight normalization. We're going to shift it to the relative to the mean. We're going to normalize by the standard deviation. This is a normalized version of the weights. And then what we're going to do is we're going to constitute a matrix, a weight matrix, gamma, which is going to be size C out times C in. And remember, that's the number of output filters and number of input filters. And these are going to be trainable parameters. Now notice that C out and C in is a relatively small number of parameters. And so gamma is not a very big matrix. We're going to just do pointwise multiplication, Hadamard multiplication. And then we have a bias. This is the modulation. This is it. Okay, so it is mean shifted and then normalized relative to the weight. And then we're going to weight each of those normalized filters by parameters gamma. So basically, if the way to think about this is that we have a collection of convolutional filters that are learned for the original image data set, here faces. When we go to a new data set, the weighting on the importance of those filters changes depending upon what the target data set is. So the filters, the K1 times K2 geometrical shape of those filters is transferred, is shared. But the relative strength of them after being normalized is target dependent. Okay, that's it. That's the only modulation we're going to do. So what we say here is that the weights, and these are just two different fonts of W for the fully connected and convolutional layers, those are frozen. Those do not change from the original data set. And then for each of these target data sets, what we're going to first do is do the normalization that I talked about. And then we will do a weighting, which will basically quantify or specify how important each of those filters is for the associated target data set. Okay, that's the idea. So how well does this work? So our we call it the source data, which is faces. Now what we're going to do is we're going to learn a generative adversarial network of the sort that I showed you. And we're going to keep the filters exactly the same, but we're going to normalize them relative to the source data set. So just mean, shift, and standard deviation normalization. So very simple. And then we're going to weight the importance of each of those filters for the target data set. And so now the same GAN model is being used after modulation for flowers, cats, cathedrals, etc. And very diverse. So you can see that these are just sketches. This is a very well. First of all, it works quite well. You might ask, well, why don't we just take the original model that was learned, the original GAN model, and let's just fine tune it for each of these downstream data sets. Now, there's two problems with this. First of all, the fine tuning doesn't work as well. So showing you here comparison of results, fine tuning versus our method. And if you look at the FID score, you can see that our result is better. But the other thing is that the fine tuning requires you to keep an entire new model for each of these data sets. Whereas with the technique that we have, we freeze those weights and only modify them by a weighting. Okay, so the idea works remarkably well. So now what we want to do, our goal was to use these GANs as memory. Hopefully now it's starting to be evident that this is going to be a good tool for memory, because we have essentially a base model, and then we're going to modulate that base model from task to task. We're going to retain our understanding of the modulation, and consequently, we will have absolutely no forgetting here. And I'll explain that some more. So this is just a repeat of that slide that I showed before. This is our goal. We want to sequentially memorize the generative process for a diverse set of data sets. It might be fairly evident now that this technique is going to be pretty good for this. So the way we do this is we build a base model using a data set that is very rich. So for example, the face data set. So what we want for our base model is a data set that is rich, is large, such that we can learn a very good base model. And that is done using data set D0. And then what we're going to do is when we go to task or data D1 through DT, the weights from the base model will be frozen. So these are frozen, these are the same. And then we're going to learn these modulation parameters, which will be dependent on task 1 through task T. We will only retain knowledge of the frozen parameters and the modulation. The number of modulation parameters is actually pretty small. And then we'll talk about in a moment that we can make it even smaller. So therefore, this is a very efficient model. There is absolutely no forgetting here, because we retain the modulation parameters from each of the tasks. And so therefore, we always have the capacity to generate data from the previous tasks. So that's what I just said. I won't repeat. So we have absolutely no forgetting. So these are some examples. So our base model is faces, and then we have flowers, cathedrals, cats, etc. And so how well do other methods work for this problem? So this is a problem that people have looked at. This thing called GAN. That's not our model. And then our is a solid model. What we're looking at here is the performance of the generative adversarial network on this task, on this sequence of tasks, where we're going to sequentially learn GAN model. The solid lines are our results. You can see we have absolutely no forgetting, and that's actually by design. If you look at these other methods, some of them do reasonably well on a single task, but then as subsequent tasks come, they essentially forget the capacity to generate data from the past. Okay, in the GAN, this is a strong baseline. It's not our model, but it's a recent recent paper. So this works well. Now, remember that our goal here is to use the GAN model for some lifelong learning tasks. One example of lifelong learning is to do multi-class classification. That is the task. And we would have different types of classification challenges over a lifetime. Okay, so and so the question is, can this model be used for that, and how would we modify it for that task? So this is again the framework. So the question is, how do we modify this setup such that we can do lifelong learning, where our lifelong learning objective is classification? And so we play the same game with an I think an interesting modification. So remember, these two W's, two different fonts, are the weights that we learn on our base model using our base data set. For the fully connected and the convolutional layer, we do a mean shift and divide by standard deviation. That's it. And then we do a pointwise product to weight the importance of those filters for the target data set. And we do that for both the fully connected and the convolutional layers. Now, imagine that at task T in our lifelong learning, we have C sub T classes. So we're doing classification. The number of classes could vary from task to task. So C sub T is the number of classes in task T. Y is a label. The data corresponds to image and label. How do we modify our generative model to account for the fact that we have labels in the task? And so this, I think, is actually kind of interesting. We were talking previously by the very good question. By the way, if there are other questions, just stop me. Don't have to wait to the end. But the question was, some of the layers have perhaps high semantic meaning and others not. The further you are from the output data, or the closer you are to the input Z, the more semantically meaningful are the parameters. And so therefore, the fully connected layer at the top has a lot of semantic meaning. And so the only modification that we make to the model is that the bias that is associated with the output of the fully connected layer is going to be dependent on the label of the image. So B is a vector of biases, and the bias will depend upon the particular label Y that we're considering, which I think is kind of nice and interesting, because the label, in some sense, is the most semantically meaningful thing of all. It's the type of class.
So Professor Carin, can I ask another question here?
Yeah, let me you can, of course. Let me just quickly do this slide and then
Sure, okay, thank you.
So just to show you how this works, all of the images that you see here are synthetic. This is a 4-class problem where we have 6 classes over time. 6 tasks over time. And we have 4 classes. And so what's happening here is there are 4 different classes, and the biases for each task are dependent upon the class, right? So that's, and you can see it produces highly realistic images. All right, so go ahead, your question.
Could you please go to the previous slide? Yeah, here. It seems difficult to understand the physical meaning of the FC BIOS. So could you explain a little bit more about it? Based on my understanding, is the error signal or something like that, or something else?
No. I mean, that's not how I interpret it. So the bias is going to be added to the output of the fully connected, and then that's going to go into a nonlinear function like ReLU, right, or something like that. And so therefore, the bias plays a very important role on the output of this layer. Depending upon what the bias is, it could have a very significant impact on the output of this layer. And so what this is saying is that the output of the fully connected layer is very dependent upon the label Y that we're interested in generating. And so now this is like turning on or turning off elements of this feature map. And then that feature map is then feeding into convolutional layer. And so, so what this is saying to me is that the output of this layer, which is a very high level layer, it's a very abstract layer because it's very far away from the data, is very dependent upon the label that we're actually considering. Does that make sense?
Okay, got it. So another subsequent question is that you already have theoretically speaking, it's also a BIOS, right? That's beta. So what's the difference between beta and your additional
so it's a big difference.
BIOS?
So good question. There's a big difference. The beta is just in. So remember what we're doing here. This part right here, these are the filters. Right, in the fully connected case, these are just the weights. And so what we're doing is we're doing mean normalization and then standard deviation normalization. And then we're just adding a bias to the weight itself, to the weight. This bias is the bias that is added to the output of the fully connected layer. So totally different thing.
Okay, got it. Thank you.
Okay, all right, but good questions. And don't be shy about questions. So I think that this actually looks quite good. So this is 3 tasks, task 1, 2, 3, and this is a 6-class problem. And you can see that, first of all, if you look at like task 1, it's bird classification, different types of birds. So being able to generate a bird is not good enough. You have to be able to generate a bird that looks like a specific kind of bird associated with a given class. Likewise, class 2 is I guess dogs. And it's not enough just to be able to generate dog. You have to be able to generate dog that looks like a specific type of dog. And then finally, butterfly. So if you look at this, first of all, the quality of the images is outstanding. There is no forgetting. And we are very good at constituting images which are characteristic of particular classes. All of this is done in a very efficient way with this model. So this is, we think, pretty nice. How well does this work? Now, as I mentioned, catastrophic forgetting is not a new problem. And there are other techniques. So there's something called EWC, which is somewhat of a classical method. And then there's this thing called mere GAN, which is, I mentioned, it's the same kind of idea to use GAN to have memory, but doesn't work as well as ours. We talked about that before. It has catastrophic forgetting. Joint, what that means is it's not lifelong learning. It means we take all the data at once and do it. And so joint is the upper bound. And the red is our results. You can see that that it performs quite well. And these are, we've compared to many methods. These are state-of-the-art results. All right, so with that, I have a few more things to say, but let me pause and see if there are any questions. Are there any other questions?
There was a question in the chat box. Do you already answer that one?
Okay, let me see.
The multiple questions, the 2 questions from the chat box.
This is very related to transfer learning. Transfer. There's a question about relation to transfer learning. So I would say it's quite related. Transfer learning and lifelong learning are very similar. The transfer learning, you might not be interested in the prior tasks anymore. You just want to be able to transfer to the future. But the same basic idea applies. Then, the question is the relationship to few shot learning or meta learning. This actually what we find is that the amount of data that you need for subsequent tasks decreases as you go forward, because you have the capacity to transfer information or knowledge. And so this indeed is very related to transfer learning. There's a question about a paper meta transfer learn. I can't comment on the paper because I don't recall it. I'd have to take a look at that. We did compare to a wide range of different methods. You can look at our paper. I would guess we compared to that. Okay, so can we do even better? Can we compress things even further? So if you think about our setup, we have a set of weights which are learned from our base model, here faces, and then we freeze those, and then we have modulation parameters, as a function of task. This is a relatively efficient model because we're only keeping the original base parameters, and then which are frozen, and then we're doing a modification of those. And the modification is relatively small in parameters, but nevertheless, perhaps we can do even better. So now let me, just so that you can understand the figure that's going to come in a second, remind you of our model. Residual blocks. Each residual block is a pair of ReLU, leaky ReLU, and convolution. We call these L0 and L1. So what we wanted to do was to examine whether the matrix. So if you look at the gamma, remember gamma. Anyway, gamma is a matrix. It's of size C out times C in times Cn. And so the question is, what's the rank of that matrix? So it's a C out times C in matrix. Maybe that matrix is relatively low rank. If it's low rank, then we can use a low rank representation of that matrix and then get even further compression. And so what this is showing is that the gamma matrix, which is our weight matrix, is in fact very low rank. And so, for example, if we take the top 65% of the singular values, we keep roughly 80% of the energy. And so what this suggests is that if we look at the weight matrix, gamma T associated with task T, what we actually have done is we have a low rank representation of that matrix where we have the left and right, eigenvectors, if you will, or eigenvectors, and then the weight or the diagonal matrix with which those eigenvectors are used is dependent upon task T. And then we have an error or a residual. And then what we do is we do a singular value decomposition of the residual, and then we retain the vectors that have high singular values. And so the idea is that the weight matrix within the context of this lifelong learning GAN matrix, this lifelong learning GAN setup, is low rank. And so what we're going to do is that we are going to represent that matrix in a low rank way, which is very efficient. And then over time in our lifelong learning, we will add singular vectors if needed, but oftentimes they're not needed. And to show you how this works, the compressed this is low rank compression. And this is, I guess, naive means doing it the previous way. And so what we're looking at is, first of all, the performance of compressed versus uncompressed. You can see that the compressed version performs relatively well. And further, the number of additional parameters that we need for the model drops off very quickly. So this is a highly efficient setup. So that's the last technical thing within the model. And then we're gonna take a few moments to just to examine some aspects of this. But before I do that, any questions? Okay, so let's there are a few things going on here. So what aspects of this model are particularly important? So we're going to train the model. The base model is going to be the Celeb data, and then we're going to consider target data of flowers, cathedrals, and brain tumor. And so there are multiple components of the model. There are the weights. Remember gamma, the two gamma and gamma, small and big gamma. They were the biases, and then they were the biases on the filters, and then the biases on the output layers. And so which of these are important? So if we only use the weights, we can see that when we do transfer from, say, faces to brain tumor, there's a transfer. You can see there's a transfer, but it's not great. If we only do the bias on the filters, it doesn't do much of anything. If we only use the output biases that we talked about, again, not a whole lot changed. And so what this is showing is that all of these together are necessary to produce the output here: flowers, cathedrals, and tumor. And then, how important, for example, are these biases? You have to look at the fine scale details, but you can see that without these biases, you do indeed lose some details. So the point of this figure or this slide is to say that all of the parameters in the modified GAN play their own role. Some are more important than others, but they're all necessary. Okay, so there was a question, a really good question at the beginning, which was which residual blocks or which layers are actually important to modify from the standpoint of semantics, and which blocks are likely highly transferable without any modulation at all. In other words, they're generalizable. So again, I show you the model so that you recall the model. So B0, so FC is fully connected. B0 is right after the fully connected, and B6 is the layer right before the output data. And so now what we're showing is a transfer from faces to flowers. And what we're showing here is that what would happen if the only thing we modify is the fully connected layer. And the fully connected layer by itself, just you don't get much change. Now, if we modify the first residual layer, we start to see some change. The next layer, we start to see significant change. The next layer, B2, which is the third layer, now it's really starting to look like a flower. Layer B3, again, improvement. And then B4, B5, B6, not a whole lot of change. You can see that as we get down to the sixth layer, maybe it looks better, maybe. But what this is telling us is that within the context of our network, the first, B0, B1, B2, and perhaps B3 These are the layers that play a significant role in the semantic context of the output image, where the subsequent layers may be important in the context of producing the final image, but those layers are transferable. They're generalizable. And if you think about this a little bit, it makes sense. I could talk for a long time about why this is true. But in any case, but rather what we could have done, what we could have done is said, well, let's just freeze the parameters for B4, B5, B6, because they don't seem to matter. But that's only retrospectively. If we were to have done that a priori, I would have been making, guesses or using intuition. And so the point is that within the context of this framework, we're able to learn which layers are important for that require significant modulation to affect the output image, and which layers are transferable in the sense that they don't change a whole lot. And so we were able to uncover that from this analysis. So I hope this answers that earlier question. Now, one of the things that we can do with this model is that we can now transfer images from one type to another. So for example, you can give me a flower and I can transfer it continuously into a cat. What we're doing here is there are weighting parameters associated with the flower. There are weighting parameters associated with the cat. Remember those weighting parameters that we learned. What you're seeing here is a smooth transition from the flower weights to the cat weights. So I think this is pretty neat. Now, the final thing that you might be asking is how important are these biases in the context of our modified model for lifelong GAN model learning. And so what we're showing you here are results when, sorry. So the question that you might be asking is how important is the normalization, and how important are the biases? And so the circle results are if we just took the weights directly and just weighted them, no mean shift and no standard deviation. What you see is there's a very significant improvement in performance by using this normalization. So this plays a very important role, and I can talk for a little bit about why that's true if there's interest in that. The biases, they play a role, maybe not as significant. So if you were to ask what is really important here for getting the good results, it's this mean shift in standard deviation normalization. The bias is less important. However, in the context of the class-dependent classification that we talked about before, the bias plays a very important role. Okay, so now this is my very last slide, and I can take any last questions. So we've developed a general lifelong learning framework. It allows us to continually learn the generative process of the data over a lifetime of multiple tasks. This framework has no forgetting. It is highly efficient. However, the technique that we're doing, it has forward transfer. If you think about this, it has forward transfer, but we're not modifying the frozen parameters from the original task. The good thing about that is we're not doing any forgetting. The bad thing is we're not doing any backward transfer. In other words, we're not modifying anything we learned from the past based upon what we learn in the future. So, open question, is there a clever way to do both forward and backward knowledge transfer? This is an open question. These are some papers. So some relatively recent papers where we published this. This is all on my website. And so that basically is my talk. I want to just show you just for fun. These are some images that were generated from this model where we're going to do continuous transfer or transition from faces to flowers, right? I showed you this before, but this is very high resolution. Here are some examples of transferring from flowers to cats. So I think this is pretty interesting. If you look at this flower and then just watch it transfer into a cat. Pretty amazing, I think. There's a lot of fun things you can do with this technology. I hope this talk has been helpful. I'm happy to take any last questions that anybody might have.
Thank you, Larry. This is a great talk. There are maybe there are many questions on the chat box. Maybe we should get in those things first before.
All right. Let me see if I can do that. Hold on. Okay, sorry. All right, let me go through the chat.
So the first one for a sequence or 3 tasks. Yeah, that one.
Yeah, so the question 3, yeah, the number of tasks can vary. I mean, sorry, the number of classes in a task can change. So the question is, can the number of labels, if you will, can the number of labels change? And the answer is yes. And we had that before. Remember, I had C sub T. C was the number of classes in task T. So yes, the number of classes can change from task to task. Yeah, so the next question, yeah, so the weights, the fully connected weights and the convolutional weights from the base model, the original, the first data set, those are frozen. And then we only learn in the subsequent tasks, we only learn the modulation of those parameters, which are in the form of the multiplicative Hadamard weight plus a bias. So the amount of learning that we have to do for downstream tasks is pretty small. And so one of the nice things about this is that the amount of data that you need for subsequent tasks is very small. So somebody had in the chat a question about few shot learning, and this technique is indeed very relevant to few shot learning. So yeah,
is the diagonal
the next one is not really about my paper, so I won't talk about that.
Larry, can I ask a question? Nice to meet you.
Yes.
I'm Chung.
Hey, Chun. Hey,
It's been a long time. Yeah. While I'm listening to the talk, it seems that the proposed technique is general for any life learning tasks, right? While in this paper, you are mainly talking about its applications on GANs, right? Which is a generative, which first is a generative task. And second, everything is built on top of convolutional neural network, right? Yes, so yes. I'm considering whether this proposed technique can be generalized to more maybe popular domain. For example, for large transformer pre-trained models, those foundation models, right? And it's especially for those understanding models such as BERT and Robota, right? So I can see 2 differences. One is the task is different. You're mainly talking about generative model, while BERT and Robota, they are mainly for understanding tasks, right? And second one is the network architecture difference. And in this paper, the proposed technique is mainly built for convolutional neural network, right? While for Burton and Robota, the network is mainly based on transformers. And do you think how well the proposed technique can be generalized to those large NLP pre-trained models?
Yeah, so so first of all, the technique is general because we're doing the technique on the fully connected and on the convolutional layer. So it's really a very general technique. And we did look at this a bit in the like with BERT and stuff. Now, BERT is a generative model, at least predicting the next word. But as you said, it also can be used, for sentiment analysis or whatever. So the thing is that it is absolutely applicable, and it is worth looking at. We focused on Chunyan, we had a DARPA project that we were working on, right? So we had to solve their problem, you know what I mean? And so we were focusing on that. So they were not interested in language, so we didn't do it. But I think you can do it. The thing is that the problem with NLP, which is the good thing about NLP, is the problem is very constrained. Like if you're doing sentiment analysis, I like it or I don't, or I like it from 1 to 5, but it's a relatively constrained problem. And then, we predict the next word. Well, okay, it's 1 of 10,000 words, something like this. Sounds like a lot, but not that much, really. To produce an image, image of an X-ray versus image of a cartoon, these are very different things, and these are very big images. And so the point is that what I think you might find is that simpler things might work reasonably well, because the problems in NLP, in some sense, are a little bit easier.
I agree with this, meaning that I agree that classification task is easier than generation, especially image generation task, because when we think about the number of dimensions when we do the final prediction, right? Yeah.
But Chunyan, where an interesting problem where this might be useful, for example, is in translation. So that if you have different languages and perhaps they use the same alphabet, they're Latin languages, but they're different. And could you like pre-train a model on English and then transfer it to Spanish, and to do that in an efficient way, so that you don't have to have as big a model. Like I can have a model for English, French, Spanish, Portuguese, and I have like a base model and then a modulated version of that base model. And the modulation is much more efficient than the original number of parameters. That would be interesting. I think that you need to, in the NLP, you need to do a problem that is fairly sophisticated. If you're doing things like it or not like it, binary, text, it's just too simple. And so it's kind of hard, I think, for these things to do well. But translation could be interesting. And the other thing, there was a question about few-shot learning. I think that this type of technology is very good for few-shot learning. In fact, this paper, this NeurIPS paper, which paper was it? This one, the second one, this ICML paper, that actually was a few-shot learning paper. That you had a small amount of data on subsequent tasks and could use this to learn very good models, and we did. So like we would take like 50,000 faces and learn a really good model on faces, and then we would get 10 images of flowers, and then we would transfer that face model into a flower model, generative model, and produce very, very nice data. Very nice generative images. And so, anyway, I think that this is a very general technique, and it could be applied to many things, I think.
Yeah, I agree. It's what was trying to see how applicable it is to other domains. Right. Thank you.
Hey, Larry.
Yes, hey, Hong Tang.
Hey, Larry. Long time no see. Nice talk. And I have 2 questions. So the firstly is this work, I think, make me remember your student Nikhil. And Nikhil did some work about Bayesian neural network, if my memory is correct. And you are also talking about how to understand this work. Can we understand this work from the Bayesian viewpoint? And because I remember Nikhil do something like Bayesian neural network and do task adaptive, something like that.
Yeah, so Nikhil, he published that last year. And so basically what we were doing is essentially a low rank representation of the model parameters. And then the low rank vectors could be transferred in a very efficient way. And the only thing that adjusted was the relative strength. And so yes, there's a connection. There's a connection, and you can look at, I think it was the AI stat paper, and he was using the Indian buffet process to do that. And yeah, it's related. It's related. You know, so what happened in Nikhil's work with the Indian buffet, you know, we were trying to be, you know, elegant, kind of Asian, whatever.
Yes.
And here we just said, look, we're just gonna throw. We just said, let's make it work. And maybe, I don't know. I think this is very kind of a simple idea in some sense, but on the other hand, it works really well. And there's actually not that much really good work on lifelong learning for GANs. So there's a lot of lifelong learning for classifiers and stuff, but for GANs, not so much. So this is a kind of an interesting framework, and as Chunyan said, also very general, very transferable, I think.
Yeah, my second question is, you mentioned that the fine tuning may be not good when new tasks comes, because from my understanding is the dimensions of freedom is too high for fine tuning. But in your case, you actually use the modulation. From my viewpoint, is introduce a lot of constraints when you want to change the parameters. And I think maybe this worker is related to some flow-based model, because the modulation, from my understanding, is a very simple operation to change the shape and the position of the distribution. So my question is it possible to introduce a more, maybe a little complicated flow-based model to achieve a trade-off between your modulation and the fine-tuning?
Yeah, it's possible. I mean, certainly that would be something worth exploring. I would say what happens is that, you know, we didn't put any constraints on the modulation parameters. Like we didn't impose any constraints on relationships between the tasks or any type of a flow. And it's possible that if you did, you could improve your results. However, you need to understand what the appropriate flow is. And so what oftentimes happens is that if you add some kind of regularization connected to flow, that's fine as long as that's accurate and correct. And then if it's not, so it's just a whole lot of extra work, and it's not always clear that it works better. Yeah. So I would say that this is an example of something where something pretty simple works really well. I mean, my good friend Yulei is on here on the call, and he and I had a fight one day, and Miao Yun, because for this ICML paper here, it was good, but I just kind of felt like it wasn't that fancy or something. So I wasn't even sure we wanted to write the paper. So we actually had a fight about whether we should write the paper or not, because I thought we should try to do something more fancy, like you're saying. And they won that fight. Thankfully, they won that fight, and they were right. The simple things sometimes work pretty well. So, you know, it's easy to say things are simple retrospectively, but nobody had done it before. It's a simple concept, and it works really well, but it hadn't been done before. And so in any case, what we found, Hong Tang, is simple concept, but some important ideas works pretty well.
Yeah, I agree with you. The simple maybe the better, but because the modulation didn't change the shape of the distribution. I just interesting. If we change the distribution's shape.
Well, it didn't change the shape of the filter, but that doesn't mean it didn't change the shape of the statistics, because the GAN is a generative model, and it is basically a statistical model, and so we're changing the statistics of the GAN output dramatically.
Okay.
But we're not changing the statistics. The shape of them, the shape of the filters is unchanged. The relative weight of them is being changed, not the shape. But the shape, when you do that, because those are internal to a very complicated model. And then if you look at the output statistics of the GAN, they change dramatically, because if you look at, we started out with faces, and then we're producing cartoons of whatever, or x-rays. The statistics change dramatically.
Okay, thanks.
Very great, very great talk. So I have a few questions. Actually, did you think about anything like because for example, graph, when you use GAN memory to generate some graph or subgraph, even connected graph, connected to graphs. Have you thought about any kind of, or do you have any suggestions on that? Because graph probably relatively not so continuous like images, or even better if you can train on images and generate language text. Have you thought about any this kind of combination?
So what I would say is what we're trying to achieve is to achieve lifelong learning and transfer learning in a way that might be, in some naive sense, consistent with how humans do it, right? So if I learn English, or another way, if I learn how to classify image type A versus image type B, then it might be easier for me to learn how to classify image type C or something. There's a relate. They're images. Now, so the point is that there's human capacity to do this, and therefore we would hope that a machine might be able to do it. When we do the transfer learning or the lifelong learning, the tasks from the past have to be related in a meaningful way to the new tasks for us to expect some sort of transfer. So, like, for example, if we, of all of the previous tasks were image analysis, and now the next task is NLP, it would be very, very difficult to do transfer. And it would be very difficult even for a human to do transfer. Because if I don't know language, looking at an image and learning a language is very difficult.
But you can do like pre-training on language, pre-training another model on image, then two models you generate. Now you want to solve another new task in text, a new task in image. Like
so what I would say is, yeah. So what
these modalities.
Yeah. So what you can do is to jointly learn an image model and a text model, NLP model. Right. And you could have a situation where you have joint image and text, and then text alone, and then image alone. That you can do. That you can do. But the transfer needs to be sensible in the sense that there is some kind of expectation of transfer.
So how about graph?
Yeah, so we haven't actually, Hong Tang, who was talking just a while ago, he's done a lot looking at graphs, but we haven't, I would say, Andy, it's a good question in a good direction. And this actually gets to what Chun Yuan was talking about. This framework that we've talked about is, I think, a pretty general framework. It's not really related to images per se. It's a general framework. What it is saying is that within a deep neural network, sometimes the fundamental structure of the parameters does not change, the shape, if you will, but there's like kind of a weighting that changes from task to task. And so we would have to study it, but I think that there could be some potential to do for graphs as well. It's certainly, I think you could do it for NLP. It's a general idea.
Yeah, actually, it's related. It's can you create something like a task? Probably can be done using the conditional. And they're trying to say like you want to create a fish. I mean, you're training on a fish. You want to generate a face. But how about two objects? One object is like a human actually looking at the fish or looking at the dog or something like. Probably can be.
Well, anyway, all I can say is the work that I presented today is relatively new, and there are all kinds of things that we could do.
Yeah, cool. Thank you so much.
Thank you, Andy. Yeah, Andy was a professor at University of Florida, in case Larry and Andy never met before. So it's good Andy mentioned about graphs, because our next talk in a few weeks will be will be given by Thomas from Google. He was the author for the GAN paper with Max Welling. So I promised that I will let Larry go before 8:30. So we still have many questions on the chat box. So maybe we just go backwards, so see whichever questions you like to answer. Or
yeah, I'm looking at that.
Yeah. If you maximize it, you will see the question better. And it's easier to go backward because you don't have to keep track of which question you already answered. Yeah, you will run out of time.
So yeah, I'm gonna need to leave in a second, but I'm looking at does task 1 to task 6 need to be sequentially changed from minor variation to large? No, the variation from task to task is really kind of arbitrary, and there was no specific order of those tasks that was selected. That we were not trying to make the change from task to task be small, and in fact, often it was not small. Because in fact, before we even did the lifelong learning, remember, we did transfer from faces to flowers and skulls and whatever, and so so the transfer could be actually from task to task could be significant, anyway, I think that maybe is captures most of the questions in some sense. Again, at the end, I can send you guys the slides, and at the end of the talk, there's 3 papers that you can read where we go into all this in great detail. I think that there's a lot more that can be done. There's no doubt about that. A lot more that can be done, and a lot of good questions and suggestions. And I do think these are all things that are worth exploring.
Great. Great. And so let's all thank Professor Larry Carin and for his great efforts to get up at least 5:30 a.m. his local time. And so now it's still very early in the morning his time. So thank you everyone for coming, and let's thank the speaker again. Thank you, Larry.
Thank you, Larry.
Okay. All right.
Thank you.
Okay, guys. All right. Thank you, guys. It's my pleasure. Okay. Take care. See you.